All right, let's solve this problem. So a person stands at the rim of a large turntable. Well, this is a turntable, this is a person. The radius of the turntable is 4 meters. It's heavy, massive. The mass is 200 kilograms. The person is much lighter, 60 kilograms. So the person makes 2 marks, one on the turntable, second on the floor, and then he starts walking. So he walks slowly. 10 minutes later, he steps again on the same mark he made on the turntable. Well, that's what's happening. So, turntable, person. If the person is walking and we hold on the turntable so it's not moving, walking on the turntable is not different from walking on a floor. However, if the turntable is free to move, what's going to happen? Well, we have two objects interacting. That's a closed system. And for the closed system, we know some conservation laws. In this situation, the turntable can rotate one way or another. And that means we could apply the law of conservation of angular momentum. So, before anything started happening, we had a turntable, person. If we look from the top, we don't see anything but just head, and everything is at rest. So for the person, the angular velocity is 0. For the turntable, it is 0, which means the whole system doesn't have any angular momentum. The initial angular momentum of the whole system is 0. After, well, the person starts walking, and well, let's say the person walks clockwise, which makes his angular velocity negative. Well, at least it's not 0 anymore. For the person, angular velocity is not 0. For the turntable, well, we don't know. What we know is, for the person, angular momentum is not 0 anymore. For the turntable, the angular momentum should be equal to this, and the whole total net angular momentum for the system should be equal to the sum of these two. Is this the law of conservation of angular momentum? No. This is just the final angular momentum of the system, and this is the initial angular momentum of the system. What does the law say? The law says that for the isolated system, the initial angular momentum and final angular momentum should be equal to each other. But if the initial was 0, that means the final also should be 0, but the final is equal to the sum of angular momentum of the person and angular momentum of the turntable. And this one is not 0, hence this one also cannot be equal to 0. In fact, if we solve this equation for the angular momentum of the turntable, that's what we get. Not 0, both. But more importantly, actually, since we know how to calculate the angular momentum for the person, for the turntable, the angular momentum of the person equals the rotational inertia of the person times the angular velocity of the person. The angular momentum of the turntable, rotational inertia of the turntable times the angular velocity of the turntable. We also call it moment of inertia. So if this guy is negative, minus times minus makes it positive, this guy should be positive, which means the motion should be counterclockwise. So when the person starts walking clockwise and we don't hold on the turntable starts rotating counterclockwise. So this arrow represents the angular velocity of the person, and this arrow represents the angular velocity of the turntable. So it might look something like this. The guy walks and the table turns. The turntable, the guy. So we can make a mark on the ground and we can make a mark on the turntable. If we hold the turntable doesn't move and the guy just walks around, and when the guy is back to original location, he is also back across the red mark. However, because when the turntable rotates, it spins in opposite direction and the guy meets the same mark at a different location. Relative to what? Well, relative to the ground, relative to the earth. Everything is happening relative to the ground. So there is another observer or like office tree. So from the perspective of the room, from the perspective of the ground, the guy doesn't make the whole revolution. And what we need to calculate is this angle. The angle by which the turntable turns relative to the ground during the whole walk. And as we know, the whole walk took 10 minutes or 600 seconds. He was walking very slowly. Well, so this is the angle, let's call it theta, the turntable makes relative to the ground, and angle over time, that's the angular velocity of the turntable relative to the ground. Okay. The guy was here, and now the guy is here. This is the angle the guy makes relative to the ground. So for the turntable, for the person. For the person, the angle relative to the ground divided by time represents angular velocity of the person relative to the ground. Now, remember we had an agreement for counterclockwise angles. Angles are positive, clockwise angles are negative, so negative angle gives negative angular velocity. But if we look at this picture, actually, if we take absolute value of this angle and we add the second angle, well, we get the total of 360 degrees, 1 revolution, 2 pi radians. This is due to the fact that we could consider this motion as composed of 2 stages. The first stage, the guy walks, but we're holding on the table. And second stage, now the table turns back and brings the guy here. So if we want to, for example, calculate this angle, what do we have to do? First, we're going to get 360. And then we're going to subtract. And that should give us the absolute value of this angle. How does it help us? Well, it helps us because we have an equation which relates to this velocity. And if we multiply each velocity by time, we get angles. So if I copy this equation, and multiply by time, well, this t represents table time. This will be the angle for the turntable. This will be the angle for the person. And we can just rewrite the person equals the equation. And by the way, this angle is negative for the person, right? So it is equal to -1 times its magnitude. So if I multiply the whole thing by -1, that gives me just magnitude of this angle. So -1 times this is the magnitude of this angle. Everything is positive now. And the second equation, we know if we add these two, that gives 360 degrees. We don't have to convert anything in the radians or revolutions. We can keep degrees on both sides. Well, because this is what we're looking for, this is what we want to get rid of. 360 minus angle of turntable. And this expression I can use now right here to eliminate one of the unknowns. So what will be my new equation? Well, the inertia for the person times 360 minus angle we are looking for is equal to the inertia for the table times that angle we are looking for. Now, a person looks like a dot. So the inertia for the person equals mass times radius squared. The radius of the circle it makes. 360 minus an unknown. And the turntable is a disk. For the disk, the inertia is equal 1/2 times mass times radius squared. Since I do it the way I want to do it, for now I just do it algebraically because it helps me to simplify things, because the radius is the same for both. Yeah. Center, radius, we can cross it out. And we also can now plug in numbers for masses. 60 for the person, 200 for the turntable. Well, 200 over 2 is 100, and 360 minus this should be equal to 100 over 60 times the same unknown. So 360 should be equal to, I take this over here, this unknown plus 0, 0, and so 5 over 3, 5/3, same unknown. Theta t is a common factor, so 1 plus 5/3. 360 equals our unknown times, well, 1 is 3 over 3, 3 plus 5, 8, 8/3. Hence the angle is 360 times 3 over 8. And I'm gonna leave it like that because I do. 360 times 3 divided by 8, 135 degrees. Done. And now you can see a short video. An example of what could happen if we try to do it. So this is a turntable, and I have a motorized cart, and if I let it go, it starts moving. Well, I will have to use my hand to turn it because I cannot turn the wheels. You can pretend you didn't see my hand, and eventually what's going to happen? This is what's going to happen. Thank you.